Welcome back, everyone. So we're in the second part of the related rates here, so we're on the third and fourth example from the notes. So we'll start with our water tank problem. So we have an inverted circular cone water tank. It has base radius 2 meters, height 4 meters. We know that water is being pumped into the tank at a rate of 2 meters cubed per minute, and we want to find the rate at which the water level is rising when the water is 3 meters deep. So we'll start with the inverted circular cone. So instead of the cone being above, the cone is kind of like the base. So our tank is going to look like this, but flipped. And we've got our radius is 2, our height is 4. And note we're filling it up with water. So we've got some water inside of there. And so we want to know how fast the height is changing, right? How fast the water level is rising up. So what we can see here, though, is that the height is changing, but the radius is also changing. So note the radius here is not fixed. So note radius and height are variable quantities here, as well as the volume of water in the tank. So I'm going to draw kind of a cross-section of what that tank looks like. So we've got our tank here. We've got our water in at a certain level. 3 meters is what we'll be interested in. So let's go ahead and label this a little bit. So we'll just note at the top it is 2. But at this water level section that we're at, it's just R. It's not a specific value. That's our changing variable. And then for the height is 4. But at the specific location that we're at where the water has filled, it's just H. So what we need to look at here is there a relationship between our radius and our height? So we know the volume's rate of change, so we can use our volume equation. So that's going to be our equation for our related rates here. So our equation is going to be the volume of a cone, which is 1/3 the volume of a cylinder. So it's going to be 1/3 pi r squared h. So note we've got 3 variables here. So if I differentiate this, let's say with respect to time, then I need to use the product rule here. So I'm going to have a dr over dt and a dh over dt, and I'm going to be adding different terms. And we probably don't want that because we don't know dh over dt, and we don't know dr over dt. So I'd really like to eliminate one of these variables. And since we're interested in figuring out dh over dt, which is the rate at which the water level is rising, then I really want to substitute r out in terms of h. And where we're going to do that is using the geometric relationship below. So we'll just make a note that r is to h, so we'll do a proportional relationship as 2 is to 4, which means that r is equal to 1/2 h, obviously, right? The radius is half the height at every particular instance that we're at. And that's going to be key because I'm going to use that in my volume equation above. So let's go ahead and rewrite the volume equation then. So volume is going to equal 1/3 pi. And now r squared I'm going to make 1/2 h squared times h. So volume is going to be, when I square the 1/2, I'll get 1/4 times 1/3. It's going to be 1/12 pi. And then h squared times h will just be h cubed. All right, so now I've got a 2-variable equation, but I know what the rate of change of the volume is. So we'll go ahead and differentiate with respect to time. So dv over dt is equal to, when I differentiate h cubed, I'll get 3/12 pi times h squared times dh over dt using the chain rule. All right, and then we can just simplify from here. So now we'll look at the known information that we have. So we know dv dt is equal to 2 meters cubed per minute and it's filling up, so it's positive. We could also have the case where we poke a hole in the bottom and we're losing volume, so the water level is decreasing, but in this case we know it's increasing. We know that we're interested when H is equal to 3 meters, so 3 meters deep. And if we look, that's all we're really going to need to isolate dH over dt. So let's go ahead and plug those two values in. So we'll get 2 is equal to 3 over 12 is just pi over 4 times h squared, so that's going to be 9. So 9 pi over 4 times dH over dt. So then I'll have 2 equals 9 pi over 4 dH dt. And then to isolate dt, just multiply by the reciprocal. We'll multiply by 4 over 9 pi. Get some nice cancellation there. And then we'll end up with dH over dt is equal to 8 over 9 pi meters per minute. And note, height is a linear measurement, so just meters, not meters squared or meters cubed. So if it were the rate of change of like area, then we would have meters squared. The rate of change of volume is going to be meters cubed, so be careful with your dimensions. So that's what we end up with for that example. Again, a very standard introductory example using cones. All right, so then the second example is going to require us to involve some directions here. So we've got car A is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for an intersection, so where the two roads intersect. At what rate are the cars approaching each other when car A is 0.3 of a mile away and car B is 0.4 of a mile from the intersection? So again, here's going to be where we need to really be careful with how we set up our diagram. So the car A is traveling west and car B is traveling north towards each other. So if we maybe make this point the point where they are approaching, we've got one car's heading west, that would be car A, and then another car's heading north, that would be car B. And then we want to know at what rate are the cars approaching each other, which means what is the rate of change of the distance between the two cars. Okay, so we'll note that car A is traveling at 50 miles per hour. So let's put what we know here. So we know, let's give these dimensions some measurements. So note, all three sides of this triangular relationship are changing. In particular, our triangle is shrinking, right? Because the cars are heading this way, so the triangle is going to get smaller as they get closer. So we can call this X, this Y, and this Z, let's say. So the vertical being Y, horizontal being X. Doesn't really matter which variables you choose, but I'm just going to use X, Y, and Z. So we know that car A is traveling west at 50 miles per hour. So dx over dt is equal to 50 miles per hour. But the distance is decreasing at that rate. So we're going to say that it's negative 50 miles per hour because this is really a vector moving to the west. And then we've got dy dt is 60 miles per hour. And if I look at the direction it's traveling, the distance is also decreasing. So note, if we had, say, car B heading south, so it was moving away, then it would be a positive velocity measurement. But because they're both heading towards the intersection, the distance is shrinking. So Z in particular is shrinking, as well as X and Y. So they're all shrinking quantities. So Z should be a negative answer as well. So dz dt is going to be a negative answer. And note, we're interested when X is 0.3, Y is 0.4, which means that at that moment, Z will be 0.5, since that forms a Pythagorean triple. So we need to figure out the equation, which should be obvious by now, is going to be the Pythagorean theorem. So, but it's going to be slightly different than our ladder problem, because remember in our ladder problem, our ladder was a fixed 10 feet in length. Now everything is a variable. So everything's a variable, but we know quite a bit of information, so I think we'll be, whoops, okay, squared, not cubed. So let's go ahead and differentiate with respect to time. So we have 2x dx dt plus 2y dy dt equals 2z dz dt. And we're interested in dz dt. So note, everything else is known at the moment that we're looking at. So we'll fill in those values. So we're going to get, and no, we could just cancel the 2's first. So the 2's will divide out, so we don't have to worry about those values. So x is 0.3, dx dt is negative 50, plus y is 0.4, and negative 60. And then z is 0.5 times dz dt. That's our unknown. So we'll do a little bit of multiplication here. So we'll get, let's see, I believe negative 15, and then 4 over 10 is going to be negative 24. Right, because 6 times 4, yeah. So, and then equals 0.5 dz over dt. And then we can just multiply everything by 2 to cancel out the half. So what we're going to end up with then is that dz dt is equal to negative 39 times 2. So that's going to be negative 78 miles per hour. Yes, miles per hour. So the distance is decreasing at negative 78 miles per hour. So even though that's the longest length, it's shrinking the fastest as well. Okay. And note, we could say if we wanted to that the cars are approaching each other at a rate of 78 miles per hour. Again, giving context to what's actually happening. Okay. So again, another Pythagorean theorem example, but now with all three portions of that equation being variables. All right, so we'll move on to the spotlight problem, or searchlight problem. So a man walks along a straight path at a speed of 4 feet per second. So we've got a straight path that we're moving along, and then there's a searchlight located on the ground 20 feet from the path, and it is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So this is an example where reading the context and building the diagram is going to be kind of the challenge of the question. So we know that the man is walking along a straight path. Right, so we've got the man here walking along the straight path. And the searchlight is located 20 feet from the path. And so we're looking when it's 20 feet from the path. But also, let's move our man maybe to the a little further down. Also, that we know that the searchlight that we're looking at is, the rate at which the searchlight is rotating is when the man is 15 feet from the point on the path closest to the searchlight. So the point on the path closest to the searchlight is going to be the straight line distance to our searchlight itself. So we know that the distance from the searchlight to the path is 20 feet. The distance from where the man is located is 15 feet. But in general, it's going to be a variable quantity because he's moving away from that location. But we'll add in parentheses here that at 15 is when we're looking. So we're going to need another right triangle relationship here to kind of figure out how fast that searchlight is rotating as it follows him. And note the value that we're interested in question is the angle made, right? So how fast is it rotating is going to be the rate of change of the angle, which we can just call theta. Okay. So looking at our values, we have some options. We could use sine, cosine, tangent, any of those sorts of things. We should add some additional what we know. So we know x is 15, and we know dx dt is 4 feet per second. So that's the speed at which he's moving along the path, which is positive because he's moving away from the searchlight. You could draw the diagram flipped and have him walking towards the searchlight, and that would slightly change kind of the values in your answer possibly. So, but you should still end up with the same rate of rotation. All right, so, oops, let's note that's not d theta, that's dt. Okay, so the relationship that looks like we're going to be using here is going to be opposite over adjacent to the angle theta, which would be tangent. So it looks like we want to use tangent. So let's go ahead and do that. So we'll note that tangent theta is equal to x over 20. And note, it might be better to write x over 20. That's probably what some of you chose to do, is 1 over 20 times x. So we don't need to use the quotient rule. It's just a linear term times a coefficient of 1 over 20 in this case. But the opposite over adjacent relationship would be x over 20. So we've got our equation. Let's go ahead and differentiate it with respect to time. And we'll get the derivative of tangent is secant squared theta times d theta dt. And then we'll just get 1 over 20 times dx dt. And now we just need to put some values in. We should probably note what secant theta is. So if we fill in our triangle, we've got a 15, 20, 25 triangle at that moment, even though the hypotenuse is a variable quantity. It's going to be 15, which this is just a multiple of the 3, 4, 5 triangle. So for secant, that is going to be adjacent over, hypotenuse over adjacent, which is going to be 25 over 20. So I think what I want to do though, so we could use that, so we could do that. So that's going to be 25 over 20 squared times d theta dt. And then we'll have 1 over 20 times 4. So let's go ahead and move that over here. And so we'll multiply by the reciprocal of that squared quantity. And we'll end up with d theta over dt equals, so the 1 over 20 times 4 is just 1/5, and then times 20 over 25 squared. And then we can just simplify that value. So we got 20 times 20, but it's divided by 5, so it's really 4 times 20. So we'll get, I believe, 80 over 625, which is going to be radians. So no, radians, not degrees, because we have no units per second. And then again, we could simplify this if we wanted to. So I think we'll get 16 over 625 is going to be 125 divided by 5. Again, radians per second. let's go ahead and double check that. So we've got 1/5 times 20 divided by 25 squared, which is 0.128, which is 16 divided by 125. Perfect. All right. Yeah, so we'll get 16 over 125 radians per second. Something to note for the AP course, we use radians pretty exclusively, so you're only going to ever use degrees if degrees are given in the problem itself. All right, so we'll do one more example here. So we've got physics application here. So we've got a particle moving along a curve, and as the particle passes through the point 4,2, its x-coordinate increases at a rate of 3 centimeters per second. So we'll underline some important information here. Then how fast is the distance from the particle to the origin changing at this instant? So this is going to be a distance measurement problem, it looks like. But we should go ahead and graph it. So we've got the square root of x. It's going to be our standard square root of x. And then we've got this particle that's at a point, and it's going to be at the point 4, 2. Okay, so at that point, we want to know what is the distance to the origin changing at. How fast is that length changing? So we can actually connect it, and then what we can see is that we're going to have a right triangle relationship here. So we should note we're going to have x here, we're going to have y, and then this we can again call z, and all three of those distances are changing. Now we know some information, so we know the x-coordinate increases at a rate of 3 centimeters per second. So dx over dt is equal to 3, and it's increasing, so it's positive centimeters per second. And we know that y is equal to the square root of x, which means that if we know dx dt, we can find dy dt just from this equation. So if I differentiate this equation with respect to time, we'll get dy over dt is equal to, so that's going to be 1/2 x to the negative 1/2 times dx dt, which is going to give us dy over dt equals, so dx dt was equal to 3. So that's going to be 3 over 2 times 1 over rad x. Okay, so we can use that later. So dx dt and dy dt we can figure out pretty quickly. And then the distance to the origin, then we're going to use the Pythagorean theorem again. So we'll note that x squared plus y squared is equal to z squared, and we want to know dz dt. So let's go ahead and calculate. So we'll get 2x x prime plus 2y y prime equals 2z z prime. So I'll use the prime notation for this. So again, if you want to shorthand with prime notation, that's fine. And the 2's will cancel again. So get that convenient cancellation. And then we want to solve for z prime. And we should note here that this distance is 4 for x. This distance is 2, which means that z is going to be the sum of the squares of those square rooted. So that's going to be radical 20, I believe, which is the same as 2 rad 5. So 16 plus 4 is 20. So we can use those values for z, x, and y. So let's go ahead and plug those in. So we'll have 4, x prime is 3. Why don't we figure out dy dt at 3? So at x equals 4. So if it's x equals 4, we'll get 3 over 2 times the square root of 4, so 3/4 centimeters per second. Yes, centimeters per second at x equals 4. So we can plug in 3/4. So we'll have 2 times 3/4 equals, and then 2 rad 5 times z prime. And again, we're solving for z prime, so we can, I think we can divide out of 2 actually before we move on again. So we have another 2 in common here, so those will cancel. That'll become 2 rad 3, or sorry, 2 times 3. So then we'll have 6 plus 3/4 over the square root of 5 is equal to z prime. So let's clean that up a bit. So 6 is 24 over 4, so 27 over 4 rad 5. Let's double check that. I think that is correct. If you left it as rad 20, your answer is going to look obviously a little bit different, but it should be equivalent to whatever that measurement is. And again, you don't have to rationalize. If you want to rationalize, you can. So you get 27 over 20 times rad 5, but you can leave it unrationalized as well. And you'll note with all these examples, I'm not really using a calculator too much. This one I did check with a calculator, but most of these examples to start with, we're not going to be using calculators too often. So try to do as much of the work as you can without a calculator, and then just refer to your calculator maybe at the end to do any simplification of messy fractions. So we're going to go ahead and stop here, and then we'll finish out the notes on that third part of the video. So again, if you have questions, send me an email, come by the office hours. Otherwise, until I see you next time.